Thanks for inviting me. I'm really glad to be here. This is one of the best workshops to be right next to the beach. I wish more workshops were like that. Just to preface, I'm more condensed matter, I consider myself. So if things are kind of confusing, feel free to interrupt me and ask questions because I might be using kind of different language than you're used to. So I think everyone here would know what a quantum computer is, but for example, IBM's quantum computer looks like this. It fits in the palm of your hand. And this top layer here is your transmon qubits. You got this layer of readout and all your wiring. And you put that in here, you hide it in this gold cylinder. Why would you do that? So you don't accidentally observe it and collapse the wave function. But more seriously, it's more for protecting against decoherence from electromagnetic noise. And what is a quantum computer good for? Well, other than getting funding, you can do things like Hartree-Fock, Monte Carlo. We'll hear about machine learning. What I'm mostly interested in is like these quantum simulations of many-body systems. And so lots of high-profile papers that come out using quantum computing. It looks like you can do a lot of cool things with it. And if we look at the history of IBM's quantum computers, it looks like it's almost following a Moore's law of doubling qubits almost every year. So everything looks great, right? Well, it can be difficult to filter the optimistic from the completely unrealistic. So when you actually try to use one of IBM's quantum computers, just straightforwardly, you get this noise. It's just zero here. And you have to do some clever tricks to get closer to that exact solution that we know it should be. So this one is using a compression based on Yang-Baxter equation. So we have to deal with this noise. And what I'm interested in is using topology instead of error correction. What I want are inherently stable qubits. And I saw this analogy by Charlie Marcus using a belt that I think is really great. So here you have a belt, and I twist it, and then I make a loop. So the number of twists in my belt, it can't change. No matter what I do to it, it's fixed. And actually, if I look locally, I can't tell how many twists there are. I have to look at the belt as a whole. It's a property of the whole belt. And to change the number of twists, I have to break the loop and unwind it and create the loop again. So what if we could make a qubit that's like the twists in a belt? So that's kind of the idea. So here, let's imagine we have some fermionic state, and that could be empty or occupied. Let's say that we could split it up into fraction, like a half an electron on the left and half an electron on the right. And so now I have this delocalized qubit. And if I do these local perturbations on one side, it doesn't change in energy. It's protected by the topology of the system. That would be an inherently stable qubit. How would you do any sort of computation with such a qubit? Well, those fractional fermions, they have what are called non-abelian exchange statistics, and it was shown by Kitaev that if you have non-abelian anyons, then you can build a quantum computer. So what is a non-abelian enyon? So let's say I have two indistinguishable particles, and I exchange them. So what happens to the wave function? Normally, one of two things happens. The wave function doesn't change. It's symmetric. Those are bosons. Or it's antisymmetric. Those are fermions. But an enyon can be anything. So this is an abelian enyon where you just get a phase. So it's abelian because the order that you do these exchanges doesn't matter. A more exotic type of enyon is a non-abelian enyon, where you have to represent that exchange with a unitary operator. And that operator might not commute with other exchanges. And so these are called braids, because when you draw it, in space-time, the world lines look like braids. And so by putting together these elementary braids, you can construct a circuit, and then that's how you make a quantum computation. So one of the simplest non-abelian anyons is called a Majorana zero mode. So what is that? So what you do is you take a fermion, take a linear superposition of like the whole and the particle so here we were looking at the even indices, and then the odd indices, I'm doing a difference. And so I can invert that relationship to get this. And if you look, these operators are Hermitian. If you do it, you square these operators, you'll get 1. They follow these fermionic anti-commutation relations. So basically what you're doing here is splitting up a fermion into its real and imaginary part. And because this is a particle that is its own antiparticle, it's called a Majorana. One thing you can do is that you can combine this product of Majoranas, and you get that it's the parity of the occupation. So if this is unoccupied, you get a 1. If it's occupied, you get a -1. What is a Majorana zero mode? It's a Majorana operator that commutes with the Hamiltonian. So the Majorana is associated with a fermion with 0 energy, and so it commutes with the Hamiltonian. So how do you get such a Majorana zero mode? The simplest model is called the Kitaev chain. So who's familiar with the Kitaev chain? Quite, yeah, okay, good amount of people. All right, so here's the model. You have a hopping between sites and a superconducting pairing also between sites. And then you have a chemical potential on site. So we can imagine this as a chain. These blue spheres are the sites. And I can imagine these fermions consist of 2 Majoranas. And so on the same site, these Majoranas are connected by the chemical potential. And then between sites, it's connected by the hopping. But if the hopping is bigger than the chemical potential, it's better to look in a basis where I create the fermions of neighboring sites. So in this basis, I end up with leftover Majoranas at the edges. And so this is how you get these unpaired Majorana zero modes. And these Majorana operators commute with the Hamiltonian. But actually, that's only if in a special parameter set where t equals delta and mu equals 0. If you move anywhere off of that parameter set, it turns out that the commutation relation becomes, you have this exponentially small correction depending on the distance between your Majoranas. And so this exponentially small correction will actually become very important later. So how would you use these Majoranas to do some sort of topological quantum computing? So let's say that I can transform 2 Majoranas into each other up to some constant. And let's say that transformation preserves the parity between those 2 Majoranas. So the transformation commutes with that parity operator. Well, if you do the algebra, it turns out that one of these transforms to minus the other, and the other one gets a plus sign. So depending on which direction you exchange it, you get a minus sign on one of them, just one of them. So we can construct Pauli operators out of this. Oh, so this is what the braid operator looks like when you do that. So we can construct Pauli operators using, in this case, I'm using 3 Majoranas, but Majoranas come in pairs, so we'll have 4 of them. There's a leftover one. And let's say I exchange 1 and 2. So 2 becomes 1, 1 becomes minus 2, and then these exchange with a minus sign, but you can anti-commute these so that it goes back to itself. So z stays the same, x goes to y, y goes to minus x. That's a 90-degree rotation around the z-axis. So by doing this exchange, I've been able to implement square root z gate. And if I do that twice, I get the z gate. I can also do an x gate. I can do a Hadamard. Okay. So that would be great if we could do this. So do Majoranas exist? Well, not yet, or else we would have topological quantum computers. So here are some ideas that people are pursuing to try and realize Majoranas in physical systems. So here we have a fractional quantum Hall state. We just talked about the Kitaev chain. There are ways to make effectively a Kitaev chain. You can also take a topological insulator, take that edge mode, gap it with a ferromagnet or with a superconductor, and at the boundary you get a Majorana zero mode. Or here's another idea. You take a Josephson junction, you put it on a semiconductor, apply a magnetic field, and you might get a Majorana at the ends of the Josephson junction. And people have been making devices trying to realize this. So I first was kind of dismissive of these fractional quantum Hall states, but after this APS last month, I think that with these advances in moiré materials, that this is actually kind of likely. So I'm excited for that. The nanowires for the Kitaev chain have been, it's been maybe a decade that people have been trying to do this. There's problems with disorder, and they're getting cleaner and cleaner and cleaner and getting better at making these nanowires. These Josephson junctions have been made pretty recently, and these look like I'm going to predict that this is probably going to be the first to do a fusion experiment. And then there's these really interesting iron-based superconductors, which is basically a topological insulator with a surface state, and that you can gap that out with a superconductor, and then you get a topological superconductor with vortices that host Majoranas. But what's weird about this system is that only like half, maybe even less, of the vortices show a Majorana, when every single vortex should show a Majorana. So people don't believe, people are unsure if these are actually Majoranas or if they're just a coincidence. And then what I'm really interested in are taking magnetic chains, growing chains on top of a superconductor, and these show signatures of Majorana zero modes. So here are some more recent results of these nanowires. So here we increase the magnetic field, eventually close the gap, and now we see this Majorana zero mode here. At least that's what they claim. And the same thing in this paper, you increase the magnetic field, close the gap, and then you open it up again, you get this Majorana zero mode. Unfortunately, that first paper got retracted, and this is just hot off the press, like around a month ago. They're under investigation for research misconduct. So yeah, the controversy over Majorana particles is eroding confidence in the field. So now, for the other people, we have to really make sure, be very, very critical about Majoranas. So this is the group that I collaborate with. What they do is you have this STM tip, and what you can do is pick up atom by atom and drop it to build these perfect chains, single atom chains. And so here they made this chain between length three atoms. So this is sub-nanometer precision that they're doing this, 3 to 40. And you see this edge state, but you also see a lot of state in the middle of the chain. So it seems like that isn't superconducting in the iron, so we can't use that. They've tried manganese, cobalt on rhenium, so next they changed the substrate to niobium. Here we have manganese, and we see this great gap, but we should see these Majoranas at the edges, and we don't see them here. Here, this iron, we kind of see an edge state, but my theory calculations show that both topological and trivial phases can show something that look like this. Now this one's so beautiful, this manganese on tantalum. You have this zero energy edge state. These Majorana, it looks like Majorana zero modes, has this nice gap. But with an STM, what you can do is bring an impurity next to that zero mode. And if that kicks the energy, then we know it's not topological. It's not protected by topology. And so they did that, and the energy moved. So it just looks exactly like a Majorana, but it's not a Majorana. Here's a little sneak peek. So now we're going into some really complicated stuff. We see this chain. We see the end states. We can do like this partial loop, and if we close the loop, now we don't have an end, and so now it's gapped. Looks very promising, but we don't know yet if it's topological or not. We'll see. Here's stuff that Microsoft does. So they're doing this semiconductor. You have this superconducting strip, and they can gate it. And what they see is what we saw before. We're closing the gap with the magnetic field, and you see a Majorana. At least that's what they say. But this is so dirty that I can't say for sure. And then, so another way to think, another way to do this is, let's say we just take quantum dots. Here's this quantum dot, and just use a bunch of gates. So we have all these gates. And if you remember, I said that t equals delta, mu equals 0 is this perfect parameter set. Let's just gate it until we see that we get this perfect parameter set. And so these are called poor man's Majoranas because they're not actually topologically protected. Any deviation from that perfect parameter set is going to move that energy from 0. Now you have that exponentially small correction that you have to deal with. All right, so if this is what I have to deal with, what I want to know is, can they still be used to make a topological quantum computer? And to do that, we need to be able to do simulations with it. So I wanted to find, is there a classical simulation for these types of systems? And so I ended up going through a lot of papers from the 60s and learning from Quantum Info to design a way to simulate these Majorana systems. So buckle up, here comes some equations, but I guess like you guys are a bit more comfortable with that. So here we have, you take the Hamiltonian, you do mean field theory, and you get what's called the Bogoliubov-de Gennes Hamiltonian. So here you have the normal part of the Hamiltonian, and then you double it looking at it in the perspective of holes, and then now you have these pairing matrices that gaps. You have the superconducting terms there. Okay, so I'm going to start at t equals 0 initially. I'm going to diagonalize it with what's called a Bogoliubov transformation, and this diagonalizes my Hamiltonian. So I'm changing basis with this unitary transformation, and now my Hamiltonian at t equals 0 is diagonal. And so these energies come in plus or minus pairs, kind of like a square root. You get to choose plus or minus. So I'm going to choose all the positive ones. So now I know what the ground state is. I just need to not add any energy. So all of these should be empty. So the ground state is just the vacuum of these excitations. And then I can add excitations to get all my eigenstates at t equals 0. All right, so schematically, here I have my ground state, and there's a gap to all these excited states. And so now let's add 2 Majoranas to this system. So that corresponds to a 0 energy fermion that I can occupy, and it doesn't add any energy, so that's degenerate with the ground state. So I have these 2 degenerate ground states. Now if I add another pair of Majoranas, I can add this 0 energy fermion to both of these, so now I have 4 total degenerate ground states. And I'm going to label this by how many 0 energy states are in it. Okay. So let's so these are the states that I'll be working with. What I need to do now is construct that ground state in a reference, using a reference vacuum. So what I mean is we need a state where any application of an annihilation operator gives me 0. So one way to do that is called the product state. So I take my bare vacuum and just annihilate all my excitations from that vacuum. So if I try to do it again by Pauli exclusion, this just gives me 0. And so now I'm able to represent my ground state in terms of my reference bare electron vacuum. Another way is to do what's called a Thouless state. So you create this coherent state of Cooper pairs. And this also works as a vacuum, but it's harder to see. But the problem with both of these states, normally, like, I don't know, for most systems, this will work for you. But when I tried to use these states, it didn't work. Why? My V in the Bogoliubov transformation was singular, and so I can't normalize it. Basically, what I'm doing is annihilating the whole vacuum. So I can't normalize it. This Thouless state, well, my U was also singular, so I couldn't construct this. It turns out like half of the time for me, both V and U were singular, so I can't use either of these. So I had to find a new method to construct the ground state, and that is called the Bloch-Messier decomposition from the 60s. So it's actually super simple. You take your Bogoliubov transformation and do a singular value transformation on it. And so these are the C and the D matrices are unitaries. And so I can change basis into these. And these are called the canonical basis. So the singular values, when you do it numerically, it's diagonal, real, and goes down in value. So like the largest values are up here, and then it goes down to 0. And when you do it on a Bogoliubov transformation, you get all ones, and they come in pairs. And you also have this V matrix. The same unitaries simultaneously diagonalize or block diagonalize these matrices. The V's come in antisymmetric pairs. And then they square up to 1. So these are the coherence factors. And now we can construct our ground state, our vacuum. So previously, we were dividing by V. We can just skip the zeros in V. We just don't include that. So it's kind of like a pseudo-inverse, if anyone knows what that is. And then you can change basis into the canonical electrons. Looks exactly like a BCS ground state. And then I can do the transformation into the coherent state. So here's the Thouless state, except where my U was singular, I just skipped those, and they're over here now. So using this, I'm able to consistently, in a stable manner, construct a ground state for a superconductor. Okay. That was a lot of work to just get the ground state, but now I'm going to time evolve it, because I'm going to exchange particles. So I need a time-dependent Hamiltonian to exchange it. So I start off, I time evolve my ground state. What I'm going to do is consider these as my time-evolved excitations. It's actually kind of backwards from what we're used to. The Heisenberg picture, the dagger would be on the left side. But the reason why is that if I apply this on this time-evolved vacuum, this U dagger cancels the U. And so these are, this is the vacuum of these particles. So when you do the equation of motion, what you get is these relations. And these are called the time-dependent Bogoliubov-de Gennes equations. Again, I had to dig into the 60s papers to find this one. All right, cool, I can time evolve my ground state. Now I want to do things like wave function overlaps or expectation values. What I do to do that is use Wick's theorem. So this is kind of how Wick's theorem, like this is a corollary of Wick's theorem. So let's say I have a vacuum expectation of 4 fermion operators. What I do is take all the contractions, combinations of contractions. If there's a crossing, it gets a minus sign. It's actually really interesting that this can be summarized as a Pfaffian. So a Pfaffian is kind of like a determinant. So you take all your contractions, you make this matrix, it's anti-symmetric. So down here is the negative transpose. A Pfaffian is kind of like a square root of a determinant. So you give it a matrix, it gives you a number. And this can be generalized. So if you have some n number of fermions and you want to get that vacuum expectation, it's just a Pfaffian where you take all the pairwise contractions and then the bottom left triangle is just the negative transpose of that. And that I found in this paper by Barbara Turhal. And when I saw that, like, I used to think if you have a Pfaffian, you're trying too hard. Or, like, why do you really need Pfaffians? But when I saw this, I'm like, I think God is a mathematician. How does it just come out that this is a Pfaffian? So that's how you can do vacuum expectation values. So let's say that I have some time-evolved eigenstate or time-evolved Fock state. It's going to be the string of operators. And if I want to do some sort of matrix element, it's just a string of operators with a vacuum expectation. So that's just going to be a Pfaffian. And so I can construct this matrix. I get this -1 to this because I have to reverse the order of all these operators in the bra. But it looks kind of daunting, but these contractions are actually very easy. They just consist of the Bogoliubov transformation. It's like U dagger V, or you just put these together. In the paper, I give you a table to like, okay, this contraction is this matrix, this contraction. So it's very simple once you understand what you're doing. But, so now we have this way to do simulations. So to summarize the steps, we do our initial Bogoliubov transformation. That's just numerical diagonalization of the BDG matrix. It's pretty small. We're going to time evolve it using Runge-Kutta. And then now to get the vacuum state, we have to do a singular value decomposition. And then to get these expectations and overlaps, we do a Pfaffian. So numerically, these are things that people have optimized so much. So I just take those algorithms and now I can do these simulations. Before I get in, maybe I'll stop for questions here. All right. So, OK, I kind of missed it. What I'm going to do now is exchange these two Majoranas. So I parked the left one down here, and now I'm moving the right one across. And the way that I'm doing that is changing the chemical potential of each site. So this is like the first proposal of how you would do braiding with these Kitaev chains by Jason Alisea. So now I can, with the simulation, I can track what's happening. And so what I'm saying, this Birch-Robledo, is this Pfaffian formula. And I also compare it with exact diagonalization just to double check that the method is working. And so after I exchange it once, the state goes back to itself, but the 0 state and the 1 state have a phase difference of pi/2. So that shows the fractional statistics. And if I do it again, I return completely to my initial state with a phase of pi, so that's a z gate that I've been able to do with this braiding operation. But what's nice is that this Pfaffian method, couple minutes, maybe even less than a minute, where the exact diagonalization in this case was like a weekend. So that's pretty nice that we can do this now. All right, so now I want to exchange the inner two Majoranas. So I'm going to bring that left one, park it down here, and then bring this right one, move it across, and then bring the bottom one back to in place of the right one. So that's going to be the X gate. So yeah, now we're at the initial configuration. So what happens when you do that once, that's a square root X gate. And so now we're in a superposition between the 0, 0 and the 1, 1 state. Or I could be in the 0, 1 or the 1, 0 state. It depends on how you encode what your 0 and 1 is. So you can look at an even parity subspace or an odd parity subspace. But the total parity, the total probability remains in that low energy subspace. We're at 100% in either 0, 0 or 1, 1. And what we see is that after we do it twice, we swap states from green to blue. And we can also look individually at the parity of the first and the second Majorana state. And what we see is that all our parities are going to flip. But what's nice is that I can keep track of how it flips. I can see that I first change the first parity, and then I change the second parity. And then I do the first parity, and then I change the second. So I'm able to keep track of what's happening during my simulation. And since these simulations are so fast, I can just throw a bunch of parameters at it. So here, when you're doing braiding, you have to make sure that you're doing it slow so that if it's too fast, you'll excite the system and go to an excited state. So you have to do it adiabatically. But what is adiabatic? What is that number where it's considered adiabatic? So we just test it all. And so here I'm doing one site at a time, moving the Majorana. Here, I'm just moving every site at the same time. And depending on how you do that protocol, we can see that there's a speed limit. So you want to be in the white area. And so it looks like what you want to do is change a lot of sites at the same time to get that speed. And one more example, we did a C0 gate. So here you can do that Hadamard, you can do a control Z gate and another Hadamard to get a controlled NOT gate. And so when we take our control bit off, what we see is that after the Hadamard, we're in a superposition. We do the control Z, we're in that superposition, and I Hadamard again, and I end up in the same state because the control bit is off. When the control bit is on, though, it swaps states. And I checked all the other elements, and we see that this works as a controlled NOT gate. But for all these results that I just showed, we were in that magical parameter regime. So now what happens when you move away from those perfect parameters? So here's showing like the chemical potential, and here's showing the Majorana moving around. And it looks like my zero energy state is perfectly at 0. But you zoom in, and you find that there's actually small energy splitting. And so now we have that small energy correction that we have to deal with. And what does that do to our exchange statistics? So when I exchange these Majoranas, I actually get a linear combination of gamma 2 and gamma 1. And it has this oscillation period corresponding to the average energy during that procedure. So if my energies were 0, then I'd have a perfect exchange. Gamma 2 goes to minus gamma 1. Gamma 1 goes to gamma 2. But if there's any sort of energy, then it's going to remain a little bit as gamma 1 or gamma 2. And when I change my braid time, I see that I can go between a perfect braid and completely failed braid. So we studied this very thoroughly. So we considered different cases. For instance, what if the energy splitting is coming from my Majoranas being too close together here? Well, that corresponds to the z-gate. So that's a dynamical phase around the z-axis. And then what I'm going to do is exchange these two. So now my gamma 1 and gamma 3 are overlapping. That's a dynamical phase around the y-axis. And so that's why we get this weird spinning, like this weird trajectory. What we want is sigma z to flip. So we have perfect flips, but we also have complete failure. We want it to be at -1. And we see that it's also rotating azimuthally around the Bloch sphere. But if we have only hybridization between the center two Majoranas, well, we're doing a square root x gate, and we're also having a dynamical phase around the x-axis. So it's rotating around this circle. And if I have really bad parameters where I have overlap between these two and these two, then we don't even get to that -1. We can't get a perfect braid. So we understand this, and so now we want to add some states to this. So like, for instance, we can add an impurity into the system, like one static impurity, and the stronger it gets, I get this bound state in the chain. The stronger it gets, the closer it gets to 0. And so if it's very close to 0, my Majorana state could go into this impurity state. And so I'm able to bring this subgap state closer and closer to my Majoranas. So what happens? Well, for instance, if I have bad oscillations initially, then adding an impurity just makes it worse. My oscillations get faster and faster. But if I had a good braid, I didn't have a good way to plot this, because if it's a good braid, this would just be completely yellow. And then if I added impurity, it's topological, it doesn't care. So all I would have is just a completely yellow plot. So that's good news. If you have a good braid, impurities don't hurt it. Some of the impurity positions wouldn't change the oscillation frequency, but it would change how long it takes to get into that adiabatic regime. So here we're going too fast in our braid. We're in the diabatic regime. But if the impurity is weak, you can do it faster. And so here's all the different positions. So if I have an impurity in the topological part, so this color here is showing how fast my oscillations are. And so if I put my impurity here or here, it doesn't change the color. It doesn't change my oscillations. But if I put it on the right side in the middle of the chain, then it increases the frequency. This is faster and faster oscillations. This is bad. It's interesting that it's better to put it on the left side than on the right. So if you have an impurity, you want to do your braiding protocol in the way that would be on the side that has the less oscillations. So you can, if you have a device that has an impurity, you can think about which way do you want to braid so that you get less oscillations. And here, there's something really interesting happening. The impurity, so I have bad oscillations. What this is saying is that the impurity is getting rid of the oscillations. So there are some magic spots that I can add an impurity that fixes the hybridization, that reduces that oscillation. Okay, so now we can add multiple impurities. So at every single site, I add a random potential. And as I increase that potential strength, the random impurity strength, then what happens is that my superconducting gap gets smaller and smaller and smaller. And I also see that my Majorana states get bigger and bigger, like split more and more in energy. We understand why that is happening. It's increasing the decay length of the Majorana wave function. They're becoming less localized. And so now we get more hybridization. So what happens when we have a nice braid in the beginning is that you get these perfect braids. We start adding random disorder, and it starts oscillating. But if we look at the low energy subspace, we're completely in the low energy subspace. So it's all adiabatic, it's just that we have hybridization, so it's oscillating. Eventually we close the gap, but it looks like we have this trend of maybe if we go slow enough, then we'll be in the adiabatic regime, but here we look at very long braid times. We never are able to reach that 100% adiabatic. One way we thought of how to fix these hybridization, these oscillations, is that, yes, we have an energy splitting between our degenerate, and so now that our ground states are no longer degenerate. But if I do it in a completely symmetric fashion so that even though it's not zero energy, they're degenerate, then what I get is that I can get rid of all my oscillations in one of the subspace where the ground states are degenerate. So by using symmetry, I'm able to get rid of, even though they're hybridized, they're still good at braiding. Cool, I'm actually doing pretty good on time. So here's one thing that we tried. So we went all the way, we simulated from the initialization, so you create 2 Majoranas, or actually we create 6 Majoranas, you pair create 3 pairs or 6 Majoranas, initialize it, do this Hadamard, so this is called the Bernstein-Vazirani algorithm, where you do a Hadamard, you have this oracle, and then you Hadamard back, and then so simple algorithm, but we implemented it, and so when you measure, you do the braid, and now you can fuse, and the way that you would see the readout of that fusion is you should see a charge. And so we look at the charge, and we see that when we braid this oracle, we get the charge here. We braid this oracle, we get the charge here. For this one, we get it on both of them. So we implemented from beginning to end a quantum algorithm and show that you can simulate classically this algorithm. Some other stuff that I'm interested in is open systems. So one thing that people are worried about is quasi-particle poisoning. One way that I'm looking at it is just injecting particles into the system. So what you would do to look at this is called the GKSL, or Lindblad equation. So you have your quantum Liouville master equation, the coherent part, and then this driven dissipative part. And this dissipation term has dissipation rate and these jump operators. And so these jump operators can be, for instance, a gain, you're adding particles to the system, a loss where the particle is going out of the system, or you could dephase it. And so I'm going to look at injecting particles. And so I'm going to add a particle to every single site. And so the perfect braid, I'm going to rotate x to minus y. So this is the 90-degree rotation around z. If I start adding dissipation, then it just goes to 0. I lose all my coherence, I guess. So I lose, it's in the middle of the Bloch sphere instead of on the surface of the Bloch sphere. So I looked at different dissipation rates, and so here we have like our best case scenario. But eventually, once you get to 10 to the minus 9 in this dissipation rate, then it goes linear. The error in that braid goes linear in the dissipation rate until you saturate to just maximum error. And so, like, if I were to try and put units on this, this would be like 1 particle per millisecond-ish to nanosecond is where I see this linear relation. Well, not 1 particle, but 1 particle per site per millisecond. Yeah, so that's the kind of stuff that I've been interested in. And so I'd like to thank Dirk Moore is my previous advisor, and Jasmine, his PhD student, helped me a lot with this. And then my group at the University of Melbourne with Stefan Rahul, and Cole did a ton of these calculations. Temba helped figure out what it all meant, and Dan did a lot of good programming. And I'd like to thank all of them, and thank you.
Any questions?
So I suppose, I mean, I've got a few questions, but so one of the things with these T-junctions, I always felt that, you know, the chemical potential in that T region could be very different.
Yeah.
And so my vague sense is at some point that'll sort of trap Majoranas there permanently, and you won't, I don't know, like, I suppose my question is, it seemed from your simulations that at least with the impurities you put there, that maybe this wasn't like a be all and end all, but I want to have a sort of a sense of like how practical do you think those T's are going to be?
Oh, I think that most people interested in Majoranas aren't going to braid. I think that braiding is really, really hard. So I think most people are focused on measurement-only quantum computing with Majoranas. So they want the topologically protected qubit, but the braiding part is the hard part. So they want the qubit, but without the braiding.
Okay, if I could follow up from that, I mean, I really appreciated your little account of the experimental literature. Do you think that there is a convincing signature of Majoranas short of braiding?
Yeah, that's every single time you think you come up with something, there's a paper that comes out like a month later saying, oh, I found a trivial system that shows exactly what you say. So it's so far, so the one that I talked about with the manganese on tantalum, I think that's pretty convincing that you do as much as you can to kick that zero energy state away from zero. And if there's nothing that you can do to move that zero energy state, then I believe that's a topologically protected state. So I think that's the best you can do right now. Other than braiding, yeah. Braiding would be smoking gun.
Some other question, Lucas?
So just the last part where you're like looking at the Lombardian.
Yeah.
So is that CN dagger like you're adding a fermion to the
Yes.
chain?
Mm-hmm.
Is there a reason why you only looked at adding particles instead of the loss and defacing?
Time. Yeah, I want to look at everything, yeah. Yeah, and I would rather look at low energy excitations rather than these local like these are local particles. It would be better if I looked at low energy gain, yeah.
If I could follow up on that question actually, is this going to be easy numerically? And
No,
what
well,
other situations would be hard?
So what I want to do is extend this Pfaffian method to Lindblad equation. And in that case, this whole theory is non-interacting so far. If I add this dephasing term, now I have four fermion terms, and then now I'm more into that. I can do like a mean field type of way of doing this. I've seen people do that, but the way that I'm doing it right now is exact diagonalization. Mm-hmm.
If there's no other question, I also wanted to ask if you have tried simulating T gates on Majorana, if there is such.
Oh yeah, yeah. Like So in this paper, we show that this looks chaotic, but we understand exactly where it will go. So we can control the way that this hybridizes. There's a smart way to do it. And we show that you can go arbitrary anywhere on the block sphere that you want to.
So them being non-Clifford gates is not a problem for this simulation?
Yeah, I think the bigger problem is how you encode your Majoranas into qubits. But I guess right now I'm more worried about the C0 gate, where I showed the C0 gate before, but that only works in the 6 Majorana case. If you try to extend it to higher numbers of Majoranas, then it gets more complicated.
You showed these plots for having an impurity. Did you also look at a constant strength disorder and how it affects the chain and the rate?
So this is I have a constant disorder strength, and then I vary the time it takes to do the braid. And so I would say that that's what this plot is showing, that the disorder, I didn't mention this before, is that, so I have a perfect braid in this yellow region, and I add disorder, and it's still perfect, and it's still perfect. And this disorder is bigger than the gap. And so you can have really big disorder. But, okay, so this is static disorder. So if I have a time-dependent disorder, some white noise, that can kick me out of the low energy subspace real quick.
Okay, let's thank Eric again.